Well, what I'd like to talk about is I'd like to give you an overview of how to assemble chemistry sets and how you can utilize our online database, QDB, to do this. And maybe as a first introduction, go down, please. Okay. Let's maybe have a look at the problem which you can tackle with simulations, or which simulations can be used to gain a better understanding. And this is that in the end, you want to use plasmas in the semiconductor industry to build up structures on very small scales. For example, such trenches where you then might want to deposit a thin layer in it. And of course, you want these layers, deposited layers, to be highly conformal. However, what you often can get is these structures where you get a lot more deposition at the top of the trench than at the bottom. And of course, you want to avoid this. And in the end, how these structures look usually depends on the kind of particles which reach the surface. There are particles which are actually deposit the species. But there are also particles which can potentially damage the deposited layer. So what you in the end want to do is to maximize the flux of the particle which help with the deposition, while minimizing the flux of particles which might damage the deposited layer. And in this case, you can use, for example, simulations to find favorable process conditions, where, as I said, you can get a high density of helpful particles and low densities of damaging particles. Because that for simulations to be actually useful, they need to be kind of reliable and robust. And in the end, each plasma simulation consists of two parts. On one thing, you have the physical model, which describes the particle transport and the electromagnetic fields formed in the plasma, for example. And there are multiple approaches to this. I mean, the best well-known are the particle and cell, or PIC, simulation, which simulates the plasma on a particle level, and the fluid simulation, where you approximate the plasma via fluid equations. There is then also the direct Monte Carlo simulation, which is another flavor of particle simulations. And there also exist hybrid simulations, such as the HPAM, which powers our own plasma simulation to a QBT, which combines the fluid and the particle approach. And the second thing you have to make up your mind to is the dimensionality of your simulation. You can use global models, which are usually used to get a rough overview of which particles are generated in a given gas mixture. And then you can increase the dimension from 1D up to 3D, which will, on the one hand, increase your computational load, so computation time and, for example, memory requirements, but which will enable, with higher dimensionality, to better simulate actual reactors. So in the end, you choose the kind of simulation which gives the best combination of accuracy and speed for your given problem. And one thing all these simulations have in common, that they also need a chemical model, which describes the chemical reactions in a plasma. And this consists of a set of species, which can be kind of categorized into neutrals, excited states, positive and negative ions, and of course electrons. And the interaction between these species is then described by a set of reactions, which can be roughly translated, categorized into electron impact collisions and heavy particle collisions. Essentially, the differences here is that for electron impact collisions, you often find a large database of actual cross-sections, which can also be calculated, which we'll hear about later today. Whereas for heavy particle collisions, you usually constrict it to rate coefficients. And what I'd like to do is to give you an overview of the kind of collisions which can take place in the plasma and how they influence the plasma densities. Let's start maybe with some electron impact collisions. And basically you see a list of the basic electron impact collisions. For example, you have here elastic collisions or momentum transfer, which are not the same. For example, momentum transfer can also include contributions of other cross-sections. However, what they both have in common is that they mainly impact the electron transport via the resulting collision frequency and contribute to the gas heating. I mean, which of these cross-sections you want to use depends a bit on the model you use. For particle-based simulations, you usually want to use the elastic collision cross-sections, whereas the fluid equations usually contain the momentum transfer cross-section. So which of these cross-sections you need to better describe the electron transport depends on the simulation you want to use. Then as the next category, we have excitation, which in case of molecules can also be dissociative. In this case, the molecules are excited to an unstable state, which then dissociates into other neutral fragments. And in first order, these determine simply the density of the excited states or the dissociation products. Then you can have dissociative attachment, which forms negative ions from molecules, and also the reverse process, electron detachment, which detaches an electron from a negative ion. And together these determine the density of negative ions or the electronegativity, which means the ratio of negative ions to electrons. And then finally, you have ionization and the reverse process recombination, which determine the ionization and recombination rate. And now, why do I say that these determine just the ionization and recombination rate and not the electron density? This is because plasmas are very complex and not everything is straightforward. When it comes, for example, to the electron density, which is one of the fundamental parameters in a plasma, this is actually highly determined by excitation and dissociation across sections. And to understand this, maybe a short excursion into plasma physics, you can here derive an expression for the electron density or ion density, which is then given by the power density absorbed by the electrons divided by the power losses from the electrons. And this here is a rather complicated expression, which can have a lot of terms. But in general, you can split this up into energy losses to the walls by diffusion and collisional losses. And this collisional loss term highly depends on the electron temperature. However, at the typical electron temperatures in plasma, so 2 to 5 eV, this is actually dominated by excitation and dissociation because the rates for these are rather much larger than, for example, ionization, whereas for elastic collisions, the energy transfer per collision is very small. And to give you an example how this looks, I made here a short simulation in a simple argon model, which only takes excitation and ionization of the ground state into account. And you see here on the left, I varied the excitation rate. And you see the higher the excitation, the lower the electron density because more energy is lost to excitation processes. You see here, it is the same with the ionization, which is also an impact, but it is actually smaller than the impact of the excitation processes. So if you do a simulation, you see that your electron density looks a bit off. You should rather turn your attention to excitation and dissociation reactions rather than ionization. For example, if you overestimate your electron density, it's more likely that you're forgetting some excitation reactions than that there is something wrong with your ionization reactions. However, what does the ionization influence? Is, for example, the other fundamental plasma parameter, which is the electron temperature. And here you can kind of make the particle balance. So on one hand, you have the electron production by ionization. On the other side, you have the electron losses to the walls and maybe an electronegative discharges to attachment. This would be kind of here the equation for a rather low pressure electronegative discharge. At high pressures, you can also get, for example, contributions by recombination. But in this case, you see that the electron density actually cancels out. And all these terms here then only depend on the electron temperature. So the electron temperature is usually entirely given by the rates for ionization, wall losses, and attachment. And you can also see this in our prior example, where we see now that, for example, varying the excitation cross-section doesn't influence the electron temperature at all. However, varying the ionization rate, you see the lower the ionization rate, or the higher the ionization rate, the lower the electron temperature, because you simply need a lower electron temperature to sustain the plasma. And you see a similar effect here in electronegative plasmas. You see as a function of power the electron temperature in CF4 discharge and here in O2 discharge, once without and once with negative ions. And you see in the simulation with the negative ions, the electron temperature is substantially higher than without negative ions because we have this additional electron loss term. So here, when you make a simulation and the electron temperature is off, you should look at your electron production and loss processes. So these are kind of the fundamental electron collisions. When it comes to heavy particle collisions, there is a whole very large zoo of possible processes. So I want to concentrate on some of the most vital ones. For example, we have the ion-ion recombination, where here a negative and a positive ion neutralize each other, which can also be combined with the breakup of one of the ions. And this is a very vital process for electronegative plasmas, because it's, you have to consider that negative ions do not diffuse to the walls in comparison to positive ions or electrons, because they are trapped by the positive plasma potential. So this is usually only loss channel for negative ions. So this kind of reaction absolutely has to be included if you have negative ions in your discharge. Another important collision are symmetric charge exchange, where simply an ion collides with its neutral counterpart and the charge is transferred to the neutral counterpart. This reaction does not change the densities directly. However, it is quite often the most important gas heating mechanism. So if you want to include the gas temperature in your calculation, these particles need to be included, or these reactions need to be included. Then you have also the asymmetric charge exchange, when ion collides with another neutral in the charge transfers, which can also be accompanied by the breakup of one of the involved particles. And apart from also contributing to the gas heating, this also changes the relative ion densities. For example, you see here the ion densities again in an O2 discharge with and without these charge exchange collisions. And you see with these charge exchange collisions, the density is transferred from O plus to O2 plus. So these reactions are important to determine the actual, the relative ion densities in your plasma. Then a fourth rather fundamental kind of reaction are neutral conversions, where two neutrals combine to form two other neutrals, or as a special case here, the recombination, where two fragments simply form a larger fragment. However, you have here to consider that this also requires a third particle, so that both energy and impulse conservation are in order. So these are usually pressure dependent, only dependent higher pressures. Of course, these kind of reactions determine the chemical composition of the plasma. Specifically, they can lead to the creation of entirely new species. One rather famous example is, for example, in fluorocarbon-oxygen mixtures, the CF radicals combine with the atomic O to form such COF species. So these kind of reactions are important to get the chemical composition of your plasma right, and to get, first of all, the radical fluxes right. And since the newly created species can have different, for example, ionization potentials or excitation thresholds, they can also change the electron dynamics. These are the kind of four fundamental reactions which occur, which are usually significant in every discharge. Then there are some which can only be important under specific circumstances. There's, for example, pending ionization, which means the ionization by excited states, either between two different excited states, or if the excitation energy of the excited state is large enough, also to ground state neutrals. However, these kind of reactions are usually only important if you actually achieve high densities of excited states, which can, for example, be at high pressures or in the afterglow. So this is one of the reactions where you kind of should check if these are actually important for a given set of parameters. And another thing would, for example, be electron attachment, a detachment where a neutral strips off an electron from a negative ion, which can also be done by excited states. And again, here it usually depends on the gas mixture, whether it's important or not. For example, O2 has a specific metastable state, which is kind of notorious for very efficient electron detachment. And you see here the density of O2 minus with and without including excited states in the attachment You see with the excited states in the attachment, the density of the negative ions is significantly lower than with these excited states. So apart from these four rather fundamental processes, we have these kind of processes whose influence highly depends on the circumstances. And this is something my colleague Martin will later talk about, how to identify which processes are important under which circumstances. Now then, how do you get about to design a chemistry set? There are essentially two approaches. One is, which I like to call the all-in approach, which means you simply collect all the data you find which are relevant for your process parameters, where you can maybe, if you have some experience and intuition, you can maybe from the start know which reactions you can neglect and which you need to include. And the advantage of this is that it's fast, relatively fast. However, it has the disadvantage that if you run into problems, it's kind of hard to identify, for example, chromatic reactions. Maybe some are missing, maybe if you use several sources, you have duplicate reactions and so on. So this is a method which is well suited for sets, well-established sets where you have sufficient data available. The other one is then what I like to call the step-by-step process, where you go through the species one by one. So you start with one feed gas, add, for example, electron reactions to this, then see which new species, for example, which ions or which other neutrals, dissociation products are created, identify maybe the one with the highest density, include reactions for this and repeat this, go through this reaction chain, repeat this for other feed gases, then add reactions between this, for example, the one between fluorocarbons and oxygen, and so on. And you go this until you reach the kind of the end of the reaction chain. And this approach gives you more control over the process. It is easier to identify missing reactions or to identify problematic reactions. However, of course, the disadvantage is that it needs some more time. So this is an approach which is better suited for new gases where you don't have that much data available. And maybe to show you now, let's see how you can use our database to start compiling your own chemistry set. You can find our database at www.quantemoldb.com. And it is a kind of collection of plasma chemistry data, which also has some tools to help you with assembling plasma chemistries. For starters, we have here under chemistries, all chemistries, we have here a list of some pre-assembled chemistry sets, which you can directly use. For example, we have this CF4O2 chemistry set. Click on one of these. Yes, for some, you find here some data, some simulation data, comparison to experimental details, for example, which will show you, for example, under which pressure conditions this set should be used. Then we have here a list of species included in the set, where you can, for example, check if all the species which you deem important are included, and a list of reactions. And if you have a Goat account, you can also download these chemistries either in a rather generic format or in formats ready to use with various plasma simulation tools. As I said, these pre-assembled sets are usually optimized for specific conditions. For example, you see in the CF4O2, we have here the CF species, O species and COF species, but what, for example, is lacking is larger fluorocarbons, which can actually form at higher pressures. So you might want to set up your own chemistry set using our database. And one thing you can do for starters is, for example, use our reaction search here to look for reactions for a specific particle. For example, if we go now with our step-by-step approach, we'll, for example, start with CF4, it maybe only look first at electron collisions which create new particles, meaning ionization, dissociation, and attachment. Can then click search, and they get here a list of available reactions. So we have here, for example, get dissociative attachment to F-. You can then open the link to this reaction, which will take you to a site where you see here, for example, the cross-section from our database, which you can download. And you can also download cross-sections with a free account, so you just need to sign up to the software. However, it is limited to 20 downloads in a 30-day period, whereas with the gold account, you have unlimited cross-section downloads. Or if your simulation uses Arrhenius parameters, you can directly take the Arrhenius parameters for these reactions. And so then you can go kind of through this reaction chains. For example, you see that CF3 is formed by lots of reactions. So you can continue your search with CF3. And you can find here a list of reactions. In search now, find a list of reactions with CF3. You can also limit it to react if you want it only to reactants or end products. So if you limit it to reactants, you really only get the reactants which have CF3 as a reactant. And so this way you can go through the dissociation chain of CF4. And for example, for a CF4 or 2 mixture, you can then also look here for neutral conversion. And you can then actually check, for example, for reactions between CF3 and O. And this will give you a list set only between where CF3 and O are reactants, which in this case, for example, leads to the formation of COF2. And so this way you can crawl through our database. Of course, for large chemistry sets, this becomes a bit bothersome and requires a lot of work. And for this, we have here this dynamic chemistry tool, which takes some of this work away. So for example, if we again start with just CF4, we can select here CF4 as a feed gas, then click here and update. And now basically in the background, what we've done before manually going through the reaction chain is now done automatically. So there's an algorithm which simply goes through the reaction chain, finds all possible reactions, and repeats this for the products until it doesn't find any new reactions. And this then gives you a list, for example, of neutral species, where you can select which neutral species you want to include. So maybe let's just start with F and CF3. You can include here excited states. Maybe we'll include these. We distinguish between pooled excited states and distinct excited states. You see, for example, here with simply F star, whereas here in these distinct states, we have all the states of atomic F resolved. However, you should also include only either pooled or distinct states. And for most applications, the pooled states are sufficient. Then we include here ions, so CF3 plus and F plus for beginners, and negative ions, where we also just limit ourselves to CF3 minus and F minus for the beginning. And then again, click update. And this will then lead you to a list of reactions where you can then go through reactions that include them, or simply click here select all. For example, for electron impact ionization, we certainly want to include everything. Vibration excitation, ion-ion combination, as I said, very important. So I'm just going to put in everything. Attachment to create negative ions, electronic excitation. Then we have a momentum transfer. Now for the elastic collisions, we use this now as the best approximation of momentum transfer, but deselect those for which we already have the electromomentum transfer. Then we have neutron conversion. And here's something you have to pay attention to, because some reactions come in two variants. You see here, this is both F plus CF3 recombines to CF4. However, in one case, we explicitly have this M as an arbitrary third body. In the other case, not. And essentially, this is kind of the low pressure limit, where this is the high pressure limit. So we should only include one of those. And for this, we go just with this one. Then we have here the electron impact dissociation and the charge exchange. So if you have then selected all your reactions, you can again download these. If you have a gold account in various file formats ready to use for simulations, or you can continue on our website. where we have, for example, a global model online, where you can test out your chemistry sets to see if the results actually make sense. So for example, you can set up here your process parameters. And I'm just going to use our standard values, so you can click run. And now the model is run live on the server. Yes, and then you get here the results. So you get here the particle densities, electron densities and temperature, and the different neutral densities. And for example, what you see here is that CF4 gets actually quite highly dissociated. So F is actually larger than CF4. What is a bit odd is maybe that the vibrational states of CF3 are higher than actual CF3. And you actually see here this warning, which says that we don't have any reactions consuming CF3 with vibrational states of CF3. So the density might be overestimated. So we can now go back and maybe until we get more data on these states, we can, it might be better to deselect them. However, on the other hand, we can now include, also go one dissociation step further and include CF2. Again, update. And then again, you see all the reactions you have selected before are still selected. So you can now, for example, then add all the reactions included to CF2. And again, this way you can kind of check in the global model and then fine tune your chemistry set. Of course, due to the select all buttons here, you can of course also practice the all-in approach and simply click select all everywhere. For rather complicated gas mixtures, I wouldn't recommend this. For example, for argon, this might be fine, or maybe for oxygen. But for larger chemistry sets, this might not be the best approach because, for example, as we've seen before, there are some reactions which come in different variants, so you might have duplicates. Yeah, and what I'd like to mention is that we're currently working on a kind of separate software tool, which will give you access to this chemistry generator and the global model in a separate semi-offline interface. So it will connect to the database, pull all the data for reactions and species, but then the reaction selection and species selection and running the global model will be done offline on your local machine. And the attempt is basically to give a better or more convenient interface with more functionality than can be realized in a browser window, and also to minimize the amount of communication between your local machine and our server to speed up all the times a bit. And this tool, this online global model and chemistry generator, is available to all users, whereas this offline tool will be made available to Gold members. And yes, with this, I'd like to thank you for your attention.